Hi, welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. Today we'll be talking about the dynamics of a quadrotor system. We're going to learn about the classical physics that is involved to fly a quadrotor. We'll see how these dynamic model plays an important role in stabilizing or controlling the quadrotor. Before starting this class, we're assuming that all the students are well aware of the fundamentals of classical mechanics and Newtonian mechanics. So why is dynamics important? Like imagine you have a quadrotor and you want to go from some space of point A to some point B. Like as you have learned from the hardware class, the quadrotor can only change the propeller speed. So how do we do this? So changing the speed to certain combination will allow the quadrotor to tilt and eventually move in space. So note that the change in propeller speed will directly change the acceleration of the quadrotor. So let's say to stop at point B, one requires to deaccelerate at some intermediate point I3. How do we do this mathematically? Depends on mass, size, shape, or we can simply call it the moment of inertia matrix. So for someone who don't know what a moment of inertia matrix is, you can assume that it's a quantity that determines on how much torque or moment is required for a given angular acceleration about some rotational axis. Think of moment of inertia as the rotational equivalent of mass, that's it. So it depends on mass distribution, and rotational axis. So coming back to the point, the trajectory that you see here, going from point A to B via I1, I2, I3 is known as bank controller. We'll talk about this bank control in part B of this class. So let's begin with the basics of quadrotor dynamics. So before jumping into the dynamics, let's first define what the frame of reference is. So we have two frame of references here, inertial frame or the world frame, which is shown in red here. And the second is the body frame, which is shown in blue. You can see that there's an O symbol which says inertial frame or the world frame, and the blue body frame is represented on the quadrotor. So the world frame O is an inertial frame which is fixed in space at some arbitrary point in the world, whereas your body frame, the second frame, it is defined as a certain point on a quadrotor. A good habit is to define it on the geometric center of the quadrotor or the IMU center, or maybe in some cases the camera center. That is totally a user choice and can be altered at your convenience. So the transformation, which includes both rotation and translation between body frame O and the body frame B, is defined as small r AB. You see that green line that goes from point O to the body frame, that's the transformation. And it changes as the quadrotor moves. So the body frame consists of three axes, all perpendicular to each other, same in the case of the world frame. So in figure above, you can see that omega 1 to omega 4 are the angular velocities of each propeller. F1 and F4 denotes the forces produced by these propellers, and M1 to M4 are the moments which is produced due to these forces. And also you can see on the left side of the image, there are R1 to R4. We call it the arm length or the wingspan, if you want to call it. So since we are well aware about the notation, let's move to the core part of the dynamics. So from classical fluid dynamics, we can say that the force exerted on a propeller, also known as lift, is directly proportional to the square of angular velocity of the propeller. So we can say that the force acting on each propeller is constant kf into some omega square. And similarly, the moment or the torque at each propeller is some km into omega square. So these constants depend on number of blades, diameter, pitch, material, air viscosity, and various other factors. But in reality, these are not actually constant and can change with change in things like temperature, aerial velocity, and things like that. So to achieve an equilibrium state, both linear and rotational in quadrotors, we need to have the net force or net torque acting on the quadrotor as 0, which is basically summation of Fi minus mg in the direction of B3 must be 0. Or similarly for moments, your summation of r cross Fi plus the summation of other moments must be 0. But this doesn't necessarily mean that it's a hovering state. But we are going to assume that it's hovering state, although it might be having some initial velocity. But let's assume for now that the quadrotor is hovering at a fixed position. So moving on. So now let's write the laws of motion for the quadrotor. Let's first write omega A in body frame. So omega, let's call it omega BA, can be written as your P B1 plus Q B2 plus R B3, where your P, Q, R are the angular velocities in the body frame. Also, in inertial frame, we have the net force MA, or we can say call it MR double dot, which is equal to 0, 0 minus mg plus RAB into 0, 0 and your net force. Note that here the capital RAB, not the small one, is the rotational matrix for transforming the coordinates from the body frame to the world frame. The summation of F1, F2, F3 and F4 is net thrust, which is applied by the quadrotor. Let's call this U1. And you remember the Euler's equation. The general form of the Euler's equation is given by m equals I into omega dot plus omega cross I omega. Now in the body frame, the net moment is I into P dot Q dot R dot, which is equals L times F2 minus F4, L times F1 minus F3, and M1 plus M3 minus M1 minus F4, minus PQR and cross I times PQR. So it's just another version for the quadrotor of the Euler equation. So we call this big matrix as U2. Note that here few of the forces and the moments are negative. This is because two of the propellers are spinning in the opposite direction of the other two. So the important thing to note here is that the entity U1 or the input U1 is in the inertial frame, whereas U2 is in the body frame. U1 and U2 will be the inputs that we will be controlling in order to change the position and the orientation of the quadrotor. More on this will be discussed in the next class. So do you remember the aerodynamic constant that we discussed, Kf and Km? So let's define a constant called gamma, such that the gamma is the ratio of moment to force. That is, your gamma is mi by fi, which is equivalent to be km by kf. So the Euler equation for the quadrotor becomes something like this. So thus we can write U2 only as a function of arm length L, a constant gamma, and all the four forces which is generated by the propellers. So let's talk about the main control inputs. So as we discussed in the previous slides, that we'll be controlling both U1 and U2. So thus this bold face U is a combination of U1 and U2, where U1 is the net force, which is your F1 plus F2 plus F3 plus F4, whereas for the moments or the torque in X, Y, Z direction, U2 would be responsible. So you can divide your controller or your input into two parts. One basically will be changing your net thrust, the other one will be changing your movement in each x, y, and z direction. It is very important to note that every control input you see here is in the body frame. This concludes the class for quadrotor dynamics. We'll learn about how these dynamic equation plays an important role for quadrotor control in the next lecture. See you then.